I think it's one that I started learning about like any issue I check. I can't remember which one it is. Yeah. was running around getting ice from my mom and my sister.
Okay, we good to get started? Ready to start? All right, you can see thumbs up in the back, good in the front, good in the back here, and good in the front. All right, very nice. All right, let's go ahead and get started. Hopefully I have the right PowerPoint, and I do. So today we're going to cover 3 analyses. Today we're going to cover partial correlation, regression, and quadratic regression. For going forward throughout the semester, we're condensing things a little bit since we missed last Wednesday. So I'm trying to sprinkle in some more analyses when we can fit them. So typically this lecture would be just partial correlation and regression, but instead we're going to include all 3. But I think we can do it. If you understand partial correlation, you should understand regression. And if you understand regression, you'll definitely get quadratic regression. They're all very similar. So it should be a good lecture today. Okay. That's what we're covering. And just making sure, can someone in the chat tell me if you can hear me? Can the chat hear me? Just type in yes if you can hear me. Okay, wonderful. Thank you so much. Thank you very much. All right, first though, I want to talk about 2 things. The first one is the first paper. So I've been having some groups ask me questions, and I'm meeting with some groups today. But I thought I would just cover some very brief things about the paper. The first thing I want to note is there is no page requirement to the paper. There's no minimum, and there's also no maximum. In the past, I've had papers, I think the shortest I've ever had is about 6 pages. I had one semester where a team turned in a 50-page paper. You do not have to do 50 pages. That is not required. But I will say most groups submit at least 10 pages. 10 pages is usually where most groups are at. There's not that many that are fewer than 10. There's not really hardly any that are more than definitely no more than 20. Like the one that was 50 was a huge anomaly. Most groups are around 10. So that's the first thing I wanted to note. Second thing I wanted to note is for writing this paper, it's usually easiest if you write it with the traditional academic model for writing an academic paper. So it would probably be easiest if you start with an intro where you just pretty much give a summary of your paper, followed by a background section where you provide information regarding what you're looking at, information regarding why what you're looking at is important. And then you have your method where you describe how you got your data, how the data was collected, and then also how you're going to analyze your data. But method, it's really important to not only say how you got the data, but how did the people who collected the data, how did they get the data? That's very important. And then that's followed by results where you provide your statistical analyses and the results of your statistical analyses. And then last is discussion. And that's where you talk about what you, in plain speak, what did you find? What's the implications of what you found? And then what should people do in the future based on what you found? So it's probably easiest to write the paper with those 5 sections in mind. Also, I'll say that I don't have any set requirements for style or formatting, but it should be formal. So imagine that you're writing to your boss or CEO. Yeah, just general business formal, nothing fancy, nothing special about that. And also you must cite correctly. You absolutely must cite correctly. Not every semester, but it's pretty common. I'll get a group that turns in a paper and they didn't know how to cite things correctly. So I do have to contact them and say hey, you accidentally plagiarized. I need you to rewrite these sections. And not citing correctly can be accidental plagiarism. That's very important to know. If you're using thoughts from somewhere else, and particularly if you're using text from somewhere else, you need to quote the text and you need to cite it. And that's usually what groups do when they get in trouble, is they'll use text from somewhere else and they forget to put quotation marks and cite it. So therefore I have to call them in, we have to have awkward conversations, and then you have to rewrite parts of your paper, if not the whole paper itself. So, okay. Any general questions about paper 1? Any general questions? Yep.
What kind of format do you want the citations for that?
Oh, good question. What type of format do I want the citations? You can do whatever format you're comfortable with. Most students do APA formatting. That's what we tend to prefer in the program, but it's whichever one you're most comfortable with. So citation format can be whatever. I prefer APA.
When you say paper 1, do we have more than one?
No, it's just one paper.
Okay.
Yes.
I was like,
yeah, exactly. I think I copy and pasted this from last year where we had 2 papers. So you're correct. Only one paper. Only one paper. Unless you want a second one.
No.
Okay, any other questions? Any other questions? Comments about the paper? Okay. And yes.
Submitted by one person with everybody's name on it, or how do you?
Sorry, say it again.
Is it submitted by one person in the group with everyone's name?
Yes, definitely do that. When you submit it, it should just be submitted by one person into the Dropbox, but make sure everyone's name is on it, certainly. Make sure everyone's name is on it. Also, if you think you're a part of a group, you should probably confirm that. I did have that one semester where a group turned in a paper and like there was one person left over in the class that I gave a 0 to, and he was like, oh, I was on this group. And I contacted the group and they're like, we had no idea. Like he no-showed everything and like didn't respond to our emails. So make sure you're a part of a group if you think you're a part of that group. Okay. Any other questions, comments? Okay, and I'm meeting with some groups after class today, so if you have any others, I'm happy to answer things after class. Okay, also homework 3 is due on Sunday now, and you do also have homework 4 due on Sunday, so you have 2 homework assignments due on Sunday, so keep that in mind. For homework 3, I've had this question about email a few times, so I'm just going to say it in class right now. So therefore, if a student asks me about this later, I'm just going to send them the video of this lecture. So if you're watching this later, I've talked about it in class, you should watch this video. So it's going to be awkward when the person watches this video later. Anyways, when calculating Cronbach's alphas, you only use the items, so do not include the scale averages when you're calculating Cronbach's alpha. And when calculating correlations, only use the scale averages, don't use the items. So very simple, very straightforward. And hopefully you got it now. And if not, you'll send me an email and I'll send you a link to this video and you'll watch it right now. Any questions about homework 3 or comments about homework 3?
I have some, but I'll wait till you get done, because you're probably gonna answer them.
Like, no, I think this is all I was going to say about homework 3. So
Oh,
you can answer
okay.
your question.
So homework 3 is the one that would have been due last week, right?
Yes, that's correct. Yeah.
Okay. So I was trying to look at your guides, which are very helpful, but,
Thank you.
and I'm thinking this is where I'm missing, because sometimes we'll say, make sure that your information looks very similar to this, but what I'm looking at, even like with the icons at the top, looks quite different than the guide that I'm looking at.
Okay.
I'm assuming this is why, so this should hopefully help.
Maybe are you using a Mac or Windows?
I'm using Windows, and I did download Jamovi
Okay, yeah.
to my computer using the original guide to get Jamovi.
Yeah. I'll send me an email. If anyone else is having that issue, let me know, because I usually don't have that issue.
Okay.
So the guide will like have the same numbers if you're using the practice example data set.
Right,
So of course, if you're using homework data set, it's going to be different numbers. Everything should look pretty similar though.
okay.
If anyone's having this issue, send me like a screenshot of what you're seeing,
Okay.
just so I can know what the differences are.
Okay.
Yep. So I'm happy to help with that. Any other questions or comments? Okay. So then if there's no other questions about homework or other questions about anything class related. Okay. Also, I forgot to mention, I hope everyone's doing well now after the hurricane. I know that a lot of people had a lot of damage, so I hope you're doing okay. Fortunately, where I live in West Mobile, I was able to avoid most of it, but I know not everyone was that lucky, I guess. So I hope you're doing okay. And if you need anything like extensions or anything whatsoever, please let me know. I'm happy to work with you. I'm happy to work things out. So if you had a house or a family that was affected, please contact me. I'll work with you. We'll figure out how to move forward from there. So. All right, so let's start the lecture. We're going to talk about partial correlations to start today. So last time we met, we talked about correlations. So you should have a background. You should remember what correlations are. But now we're going to talk about partial correlations. Okay, so we're going to go back to this chart that we looked at for the first time last week. And on this chart, we talk about how we start with looking at the question, are you explaining either the relationship between variables or the differences between groups? That's the first thing you should ask yourself. And as you'll see, we are sticking with looking at the relationship between variables. We're sticking with looking at the relationship between variables. We're not moving into the differences between groups yet. That will probably be on Wednesday. Instead, we're sticking with the relationship between variables. And then you should ask yourself, how many variables are you studying? Last week, we started with just 2, correlation. So now we're going to move on to only 2, but controlling for others. So now we're going to move on to only 2, but controlling for others. So we're still primarily only interested in the relationship between two variables, but we're adding this controlling for others element, and we're going to talk about what that means. So we're looking at only two variables, so we want to control for others. Okay, and as we learned last week, correlation allows us to analyze the relationship between two variables. So therefore, partial correlation lets us analyze the relationship between two variables while controlling for others. So we're still looking at something that's relatively simple, like x to y, but we think that there might be something like a, b, and c that we should account for. So we're still looking at the main relationship we're interested in is still just two variables, the relationship between x and y, for example. We might have these other variables we think might be important to account for, so we want to control for them. So whereas this is the relationship we're primarily interested in, we do think A, B, and C might have some type of an effect, so we need to control for A, B, and C to truly understand what's going on between x and y. So therefore, what does it mean to control for others? Therefore, what does it mean to control for others? I've already said that word 10, maybe 20 times. When you control for a variable, you eliminate the variance it explains in the other variables. When you control for a variable, you eliminate the variance it explains in the other variables. And by doing so, this allows us to find the unique variance shared between those two variables while eliminating, and we're keeping it simple at this point, while eliminating the variance explained by the third. So in this example, let's make it simple. Let's erase A, B, and C, and just make it A. So we might be interested in the relationship between x and y, but we want to account for the variance in this relationship that's explained by A, or we want to account for the variance in both x and y that's explained by A. So therefore, we would run a partial correlation. Whereas a correlation would just be if you're only interested in x and y. A partial correlation is if you're interested in x and y while accounting for the variance explained in both of those by A. We'll see that on the next slide. So if you're watching via the video and you can't see this too well, this will be on the next slide or maybe the one after. One way to think about this is a correlation is a marker that doesn't work. A correlation is a little bit better. A correlation is, there we go. A correlation you can think of sort of like a Venn diagram. A correlation is sort of like a Venn diagram, where we might have x and y, and a correlation tells you how much overlap there is between those two constructs. A correlation will tell you how much overlap there is between those two constructs. So with just a basic correlation, you're just seeing how much overlap there is between x and y. However, a partial correlation is when you think A might share some variance between x and y, so you want to account for A. So therefore, you also measure A, and then a partial correlation will take out the variance that's explained by A. A partial correlation will take out the variance that's explained by A. So therefore, we have A down here. We're taking out that variance that's explained by A, and that just leaves us the variance left over between x and y that is not explained by A. So therefore, this gets us, in some instances, a better perspective of x and y, but the safest way to phrase it is just, it gives us the relationship of x and y while accounting for A. Any questions about that so far? Any questions about that? Okay. So in other words, it can allow us to identify the relationship between two variables while taking away the effects of another variable. So it can allow us to look at the relationship between x and y, which is their overlap if we're thinking about it as a Venn diagram, and then it takes away this variance that's explained by A. That's another way to think of it. All right, so for people watching online, this is, I think, the darkest marker I have. So therefore, this right here is exactly what I just drew on the board. This right here is exactly what I drew on the board. So as you see in this picture up here, we have x and y. We can see where x and y overlaps. But what a control variable does is it takes the variance explained by that control variable. So it takes the circle of the control variable and takes that variance out. So then you're only left with the overlap between X and Y. You're then only left with the overlap between X and Y right there, because you take away this variance explained by this circle. And hopefully people watching online can see that now, because this is the darkest marker that I have. Okay. Also, another thing to note is we can perform a partial correlation with multiple control variables. We can perform a partial correlation with multiple control variables. So like we said before, we might not only be interested in the relationship between X and Y while controlling for A, we might also want to control for B. We might also want to control for B. So we might be interested in the relationship of X and Y while controlling for both A and B. If you want to stick with this Venn diagram approach, let's pretend B is really, really tiny, just to make it simple. So we might also control for B, and that might look something like this. So therefore we have right here still the overlap between X and Y. This is still the unique shared variance between X and Y, but now we're taking out the variance of A and also taking out the variance of B. So then the correlation that's left over is the unique variance, the unique relationship between X and Y, while taking out A and B. So therefore we can perform a partial correlation with multiple control variables, and theoretically you can have as many control variables as you want to. Theoretically, you can have as many control variables as you want to. So you can control for A, B, C, D, all the way through the alphabet. And that's another visual representation of that. So exactly what I drew on the board is that you have two control variables. You can take out the variance they explain, and then you're only left with the unique variance shared between X and Y. Okay. Another thing to note is this still abides by the same rules as a correlation. So a partial correlation might tell you the relationship between X and Y. Well, yeah, so this isn't what I have written on the board, but it still abides by the rules of a correlation. So a correlation will tell you the relationship between an X and Y, but it won't exactly tell you if it's causal. It won't exactly tell you if it's causal. So if you have cross-sectional data, if you have like the example we used before, ice cream sales and murder rate, and you do a partial correlation while controlling for something else, that's still not necessarily going to show you a causal relationship. It might still just show you a correlational relationship. So therefore, when doing a partial correlation, still keep in mind that you have to adhere to the same rules as a correlation. You can't just find a partial correlation and claim causality. You still have to satisfy the other requirements for causality. And then also the other thing I should note is a partial correlation will tell you the relationship between X and Y while controlling for the other variables, but it will not tell you the relationship of these other variables with X and Y. A partial correlation will not tell you the relationship of these other variables with X and Y. And that's why I kept on stressing before, when you do a partial correlation, you have this focal relationship you're interested in. You might have this focal relationship of X and Y that you're interested in, and you need to designate your focal relationship because that's the only result it's going to give you. Because this is the only result it's going to give you. It's only going to give you X and Y while controlling for A and B. It will not give you the result of A with X, with A with Y, with B with X, with B with Y, etc., etc. It only tells you the focal relationship you're interested in while controlling for the other variables. So therefore, you need to designate what you think the focal relationship is and exactly what you want to control for in that focal relationship. Of course, you could then just turn around, and I'll use the black marker. You could then, if you wanted to, just conduct another partial correlation with something like A and Y while controlling for X and B. You certainly could do that for every combination to know every possible relationship while controlling for all the other variables, but that would require you to perform separate analyses. This is a separate analysis from that. So you would therefore have to conduct separate analyses if you want to look at these different relationships. And that's because a partial correlation will only tell you the numerical result for the relationship of interest when controlling for the others. And if you want to look at the results for these other relationships while controlling for these other variables, you have to reconduct the analysis every time. Okay. So questions you might have would be something like, when would we use a partial correlation? Why do we care about this? Why do we care about controlling for these other variables? This is not always the case, but two instances that are pretty common in business, particularly in management. If you think a certain variable is confounding your observed relationships, if you think a certain variable is messing up your observations, if you think a certain variable is biasing your observations, you might want to run a partial correlation. You might want to run a partial correlation if you think a variable is messing up your observations or messing up your relationships of interest. So one example of this, I'll erase this to keep it simple. So one example of this might be if I'm working somewhere in HR and I give my company a employee satisfaction survey, and I want to see, well, what's the correlations of employee satisfaction? What does employee satisfaction relate with at my company? So therefore, I might want to look at the relationship between X, employee satisfaction, and Y, let's keep it simple, same thing we looked at all semester, job performance. The relationship between employee job satisfaction and employee job performance. But one thing we often believe might bias that relationship is social desirability. As we know, people might lie on their survey and they might not tell the truth about their job satisfaction. There might be biased reports of performance. So therefore, we might want to control for social desirability. Because we can assume, or we can hopefully, hope, that if we take out that variance of social desirability, we can get a more accurate depiction between job satisfaction and job performance. And you see that quite often. You'll see that quite often. In research, it's pretty common to measure job satisfaction with a Likert scale, measure job performance with, let's say, supervisor ratings, and then get a self-report of social desirability. And you kind of have to be sneaky with it. You kind of have to ask questions that people don't instantly think, oh, this is measuring social desirability, because otherwise they would lie about it. So you need to give us a scale that gets at social desirability in a little bit of a sneaky way. So common questions on the social desirability scale might be something like, I always tell the truth. No one has always told the truth. No one in the history of the world has always told the truth. So if you're someone who says, yes, absolutely, no matter what, I always tell the truth, you're engaging at least somewhat in social desirability. You're engaging at least somewhat in biasing your responses. So if you can somehow measure biasness in responses and then control for that, hopefully you can get a more accurate depiction of the relationships you're actually interested in, if you can control for that social desirability. Any questions about that one, or any questions about anything so far?
So doing that, would you use the averages of those two then instead of, you wouldn't use the inner item where your reliability, you use the averages of like the social desirability questions and the job satisfaction questions.
Exactly correct. Yep. So for all of these, we would look at the scale averages. For all of these, we would look at the scale averages. So this might be the average of the job satisfaction scale, the average of the job performance scale, and then the average of the social desirability scale. So yep, that's a good question. We would use the scale averages. Any other questions or comments about this so far? Okay. And then the other instance we might want to use partial correlations is if a third variable has already been shown to significantly relate to one or both of the variables. If a third variable is already established as being extremely important in explaining this outcome, then therefore you might want to control for it because you already know it's important. You already know that it predicts this outcome. So therefore, anything new you want to add, you should be looking at the effect of the new thing beyond what's already established. The relationship between the new thing and your outcome beyond what we already know predicts that outcome. So one example of this, once again, looking at employee job performance, is we already know that conscientiousness predicts job performance. It's already well known that conscientiousness predicts job performance. Your personality trait of how hardworking you are, of course that predicts job performance. So therefore, if you want to try to make a selection system, or maybe you want to do a research paper where you're trying to say, hey, I found this cool new thing that predicts job performance, you typically would have to show it predicts job performance above and beyond conscientiousness, above and beyond what we already know predicts job performance. So therefore, we would use we would use a partial correlation in that example because we need to show what our new thing predicts in the outcome beyond what we already know predicts that outcome. Any questions about that one? Okay, so moving on. All right, and those were the examples I just gave. So if you want to review the examples, they are in the PowerPoint. And then that's the other example, so you can review that if you want to. Okay, and then that's all I have for partial correlations. Are there any questions about partial correlations? Okay, so then moving on to regression. Now we're moving on to regression. Okay, so now we're going to go back to the chart since we're looking at a new analysis. So that's everything we're going to cover about partial correlation. So hopefully you understand this concept right here, because it's going to come back up with regression. So with regression, we're still looking at the relationship between variables. So we're still on this side of the chart. So we're still looking at the relationship between variables. But as you can see, we're no longer looking at just two variables. We're no longer looking at the relationship between just two variables. So now we're looking at where correlation was only two, partial correlation was only two while controlling for others. Regression is typically when you're looking at many predictors in one outcome. Regression is typically when you're looking at many predictors in one outcome. I will say we will start this lecture about regression by only looking at one predictor and one outcome, because that's the simplest form of regression. But typically when you're using regression, you're looking at many predictors and only one outcome. Okay, and that's exactly what I said right there. So correlation is used to determine the linear relationship between two variables, and regression is used for a very similar purpose. Regression is used to determine the linear relationship between an outcome and its predictor or predictors. So like I just said, with regression, you could have one predictor or you could have many predictors. So therefore, when we're analyzing regression with just two variables, with just an outcome and just one predictor, it's almost identical to a correlation. It's almost identical to a correlation when you only have one outcome and one predictor, because you're just looking at the linear relationship between your outcomes and your predictors. So therefore, when you only have two total variables, it's pretty much exactly what a correlation is. Okay. One thing to note about regression that's different from correlation, however, is typically when we're using correlation, we discuss the variables in regards to correlation. As I drew up here before with partial correlation, this is a double-headed arrow. And I kept on using phrases like they relate to each other. I said the two variables. I didn't say outcome and predictor. Whereas on the other hand, when we're looking at regression, we tend to discuss the variables in regards to prediction. We tend to discuss the variables in regards to prediction. So whereas correlation, we were just talking about relating to each other. There wasn't an outcome, there wasn't a predictor. With regression, we tend to talk about things in regards to prediction. And we tend to have a designated predictor and a designated outcome with regression. So whereas correlation was a double-headed arrow, regression is a single-headed arrow because we have a designated predictor and we have a designated outcome. Of course, our predictor being X and our outcome being Y in this example. So that's one important thing to note is we typically use this language. I will say that the same rules of causality still apply. It's still, you theoretically can't support a causal relationship if you have something like cross-sectional data, if you don't explain for alternative explanations. However, we still use this causal language when we use regression because that's how regression is designed. Okay. So because of this, whenever we're performing a regression, we need to explicitly designate which variables are our predictors and which one is our outcome. Whereas with partial correlation, it didn't matter the order between X and Y. With correlation or partial correlation, X and Y is the same as Y and X. With regression, that's not the case. With regression, it's important which variable is on which side of this arrow because you have to designate the predictors and which one variable is the outcome. And that will change your equations. That will change what you're looking at. So with regression, it is important what order these variables are in. Okay. Also, and you probably picked up on this already, we tend to use the term predictors or explanatory variables for our independent variables. So the things on this side are our independent variables. And for our independent variables, we tend to use the term predictors or explanatory variables. Whereas things on this side of the equation or on this side of the arrow are our dependent variables. And we tend to call our dependent variables our outcomes or our response variables. I believe the textbook used the term explanatory variables and response variables. I tend to use the term predictors and outcomes. But it's important to know that things on this side of the arrow are independent variables, and things on this side of the arrow are dependent variables. So we like to assume that things over here predict or influence things over here. Okay. And there's another visual demonstration. So if you need to look at another visual illustration, it's there in the PowerPoint for you to review. Okay. And that's what I said before. Although we use these terms predictor and outcome, the same rules of causality apply. So you could collect data on, once again, ice cream sales and murder rate. You could run it through a regression, and it'll probably tell you that the predictor of ice cream sales predicts the outcome of murder rate, but the same rules of causality apply. That even though it designates these as predictors and outcomes, it will give you results as if they are predictors and outcomes. You still have to satisfy the other rules of causality. You can't collect cross-sectional data and try to claim causality, and you have to explain, or you have to rule out alternative explanations. You would have to rule out alternative explanations, such as in the example of ice cream sales and murder rate. You would have to rule out temperature as a possible explanation for those relationships. Okay. And then, like I said before, also, regression is most often performed with many predictors in a single outcome, but we're going to start by performing regression analysis with a single predictor and a single outcome. So we're going to start with this right here, a single predictor and a single outcome. Okay, and that's what I said before, is regression with two variables is very similar to correlation. We just try to find a linear relationship between those two variables. And just like a correlation, with a correlation, we try to find the R, or the correlation coefficient, that best describes the relationship between those two variables. Regression is a tiny bit more complicated than that, but only a tiny bit. And you'll see in these figures, I believe it's on the next slide. We're in 2 slides. So regression also tries to find the test statistics that best describe the relationship between two variables. So as correlation would only give you one test statistic, as you see on underline and bolded, that S, regression gives you multiple test statistics that describe that relationship between the two variables when you're looking at a single predictor and a single outcome. So therefore, regression tries to find the test statistics that best describe the relationship between the two variables. And these test statistics are in this formula right here. So the results of a regression analysis are represented by the following formula, and this is very common. This is what you'll see in your textbook, in academic research, also in professional practice. The results of a regression equation will look like this, where it's y hat equals beta naught plus beta 1 times x. So this is what the results of your regression will look like. The results look like y hat equals beta naught plus beta 1 times x, whereas y hat is the predicted values of y. So y hat is what we predict y is based on your betas and your x. So just from looking at this equation, based on what you might remember from geometry or other classes you've taken, can anyone tell me what beta naught and beta 1 is? Can anyone guess what beta naught and beta 1 is in this equation right here? Yeah, so why would you think that? You're correct. So yeah, there you go. Yep. So put those two together. Yep. So this formula right here, beta naught is the intercept, beta 1 is the slope, and it works because we're looking at the linear relationship. We're looking at a line. We're looking at the linear relationship. So this is just simply the formula of the line that describes the relationship between x and our predicted values of y. So good job, you two. Good job. So this is just the equation that tells us the relationship, the linear relationship between x and our predicted values of y. So therefore, y hat is the predicted value or values, x is the predictor. Oops. Yeah. Let me back up in case you need to write that. So therefore, in this formula, y hat is the predicted values, x is the predictor, and like we just said in class, beta 1 is the slope of the linear relationship between the two variables. Beta 1 is the slope of the linear relationship between the two variables. In your beta 1, you can think of it very similarly to your correlation coefficient. Beta 1, you can think of it very similarly to your correlation coefficient. So when we did correlation before, we talked about positive, negative, things that were positive values are a positive relationship, things that are negative values are a negative relationship, that still applies for beta 1. That still applies for beta 1. Because beta 1 tells us the slope of the relationship. And then on the other hand, beta naught is the intercept of the linear relationship between the two variables. Beta naught is the intercept of the linear relationship between the two variables. So once again, this is just the equation for a line because we're looking at the linear relationship between x and y. We're looking at the linear relationship between x and the predicted values of y. So beta naught is the intercept, beta 1 is the slope. So what does this mean in practice? I think the next slide is what I was thinking was coming up. Yeah, there we go. So this is a visual illustration of this regression equation right here. This is a visual illustration of that regression equation right here. Okay. So on this image right here, we have a scatter plot. As we see, we had observations. We had people that scored x of 1, y of 2, x of 2, y of 3, x of 3, y of 4, and et cetera, et cetera. So all the dots or all the points are actual observations between x and y. And then our dotted line we have is the estimated regression line between x and y. So it's our predicted values of y when we plug in x based on our regression equation. And our regression equation is right here. So as we just talked about, so the first part of that regression equation, y equals, is beta naught. So in this equation right here, our beta naught turned out to be 1. So in this example, we took our data, we ran a regression. This was our resultant regression equation. So our beta naught is 1. Where is 1 reflected in this figure? Where is 1 reflected in this figure? Say it again, but louder. Exactly correct. Exactly correct. Because beta naught, this is beta naught right here. Beta naught is the intercept, so it's where the line intersects with the y-axis. It's where the line intersects with the y-axis. So therefore, in this example, our beta naught was 1, and that's exactly reflected right here. So we could instantly, without knowing what this, if we didn't know what this figure looked like, we could look at our beta naught and know where the line intersects with the y-axis. Okay, so that's how the beta naught is reflected. We then see our beta 1 is next to our x value. So this means our beta 1 to get this line is multiplied by x. So where is our beta 1 reflected in this figure? Where is our beta 1 reflected in this figure? So beta naught was the intercept. Where is our beta 1 reflected in this figure? It is the slope. So what is the slope? Sorry, say it again.
1 over 1.
Yeah, exactly. So it's 1 over 1. So it's pretty much the line itself. It's pretty much the line itself. So beta naught is the intercept. Beta 1 is the slope. So it's pretty much the line itself. Our slope is how much you multiply each value of x by to get the corresponding value of y plus the intercept. So once again, the slope is how much you multiply your value of x by to get the corresponding value of y when you add the intercept. Okay, so we could run a regression. We could get this formula. We can plot this line. So based on our regression result, what's something we would say about the relationship between x and y? So just based on what we have here. What's the simplest thing we could say about the relationship between x and y? Clear. Yeah, it's positive. Exactly. That's what I was looking for. So we see it's positive because of this figure. We see it's positive because we have a line that's increasing, that's going up. If we're looking at our regression result, if we're looking at our regression equation, what would we look at to know that the relationship between x and y is positive? What would we look at in our regression equation to know that the relationship between x and y is positive? Positive slope, which would be? There you go. Yep, exactly. Exactly correct. So we would look to know if the relationship between x and y is positive. It would have to have a positive slope. And in our regression equation, our slope is beta 1. In our regression equation, our slope is beta 1. So therefore, whenever we run a regression, once again, we think of beta 1 pretty much as the correlation coefficient. It's very similar to a correlation coefficient. So to know if there's a positive relationship between X and Y, we would just look at this value right here. We would just look at beta 1. So if this is positive, we know it's a positive relationship. And if it's negative, we know it's a negative relationship. Okay. Here's another question. Here's a tough one. So let's say we were interested and we ran our regression, we even made our chart. Let's say we actually wanted to predict some values of Y. So let's say we're looking at the relationship between job satisfaction and job performance. And I said that if I have an employee, hypothetically, that scored a 10 on job satisfaction, I wanted to try to estimate what their job performance would be. How would I go about doing that? How would I go about doing that? So once again, I have an employee with a job satisfaction of 10. I want to try to estimate what their job performance would be if they had a job satisfaction of 10. And this is a hypothetical employee. I hypothesize if I had job satisfaction of 10, what would their job performance be? And I'm going to use my regression results to try to estimate that. How would I do that?
You would plug in your value into X instead of Y, which is your result.
Exactly correct. 100% correct. So good job. To estimate a value of Y based on X, we would run our regression equation in our data. We would run our regression using our data, and it gives us this formula. And this formula can be used for prediction. This formula can be used for prediction. And regression is used all the time in business for prediction. Regression is used all the time in business for prediction. Probably the most common practical application of regression in business. Because we could collect a data set, we could run our regression, we could get this formula, and that can give us an estimate of what the outcome would be based on hypothetical values of the predictor. That can give us an estimate of the outcome would be based on hypothetical values of the predictor. So in this example, let's say we're interested in job satisfaction of 10. We would just plug in 10 for X. We would just put in 10 for X. And that would give us the equation Y equals 1 plus 1 times 10. Y equals 1 plus 1 times 10. So we would just solve the math right there, and that would end up giving us Y equals 1 plus 10, which then of course would give us Y equals 11. So it would just give us Y equals 11. So to predict the value of the outcome based on a hypothetical value of the predictor, we just plug in the number we're interested in and then solve for Y. So in this example, if we assumed, or if we had wanted to estimate what job performance would be based on job satisfaction of 10, the answer would be 11. The answer would be 11. Any questions about that? We will look at another example, but are there any questions about that? Okay. Yes?
Beta not, is that like not NOT?
Beta not, I think it's NAUGHT, like not.
Okay.
Yeah, yeah. So like beta not, like, yeah. NAUGHT, I think is how you spell it.
And when you say beta 1, does it change with the number? Beta whatever?
Yes, and we'll get to that in a few slides. So good question. So beta 1, it's associated with, so we have Y hat equals beta naught plus beta 1 x1. It's associated, our beta numbers are associated with our predictors. So our first predictor is associated with the beta of 1. So it's beta 1 x1, x1 being our first predictor. So it's where when we get to multiple regression and we have multiple predictors, our beta 1 will be associated with our first predictor, whereas our beta 2 is associated with our second predictor, and then so on and so on. So good question, very good question. Any other questions or comments at this point? Okay, so let's look at another example. So clear all drawings. Okay. Next one. So this one is very similar. So looking at this and knowing nothing else about this other than what the picture looks like, what the equation is the relationship between X and Y positive, negative, or null? Yeah, it's positive because we see both the line is going up, but also the beta associated with X is positive. So we know it's a positive relationship. And then let's say in this example, I wanted to estimate Let's use a different example. Let's say this is the number of commercials you ran and the number of TVs you sold. So X being the number of commercials you ran and Y being the number of TVs you sold at your company. So let's say we ran 200, or not 200, let's say we ran 20 commercials. Let's say we ran 20 commercials. If we wanted to estimate how many TVs we would sell based on running 20 commercials, so first off, how would we do that? Yep, so we plug in 20 for X, we plug in 20 for X, and then we would solve for Y. So in this example, if we ran 20 commercials, if we ran 20 commercials, how many TVs would we be expected to sell? Yep, 290, because we plug in 20 here, so 20 times 10 is 200, plus the intercept of 90, so we'd estimate we would sell 290 TVs. So based on this, we could estimate, should we do more commercials? Should we do less? Then of course we would do a cost-benefit analysis depending on the cost of the commercial, and then based on how much profit we would make for the TVs. Okay. And then the last example is this positive, negative, or null relationship. Yep, negative relationship. And then I'm not going to get you to figure out anything with decimal numbers at this point, or at least not in class. You might on your homework. I'm not going to expect you to be able to do it in your head right now. But we could plug in other values for X and then estimate values of Y. I will say there is one thing I want to point out about this figure is this typically is more accurate to what a regression line looks like. On the prior examples, I made it as easy as possible where all the observations were on the regression line. That never happens. That never, ever, ever happens. You never have data that's perfect. You're never going to have an instance where all of your observations fall exactly on the line. Whereas this is going to be closer to what your actual data will look like. And in fact, even this is too perfect. You'll very rarely see anything that looks like this. But as you see, once again, regression is very similar to correlation. Your regression makes the line of best fit. Your regression makes the line of best fit. So therefore, it's not expected for all your values to fall on the line. You're going to have deviations. You're going to have deviations from the line. So therefore, if you were to draw your regression line, there will be deviations. But it also means your predictions are not going to be perfect. That also means your predictions are not going to be perfect. Your predictions are going to be somewhere on this line. But since there are deviations, your line is just the line of best fit. It's not a line of perfect fit. So therefore, when you're using regression, if you try to use it to make predictions, you're still going to have a margin of error. You're still going to have a margin of error. Okay, and then there's another example you can go through on your own if you want to and try to figure out some numbers of Y if you plug in X. But once again, as you can guess, this is what a null relationship would look like. This is what it would look like if there's no relationship between X and Y. As even though there's a tiny slope, even though there's a little tiny slope right there, it's very minimal. It's very minimal. So in this example, if we were to run this regression and then calculate our statistics, this would probably not be significant. It would probably be a null relationship. It would probably be no relationship. Okay. So that's pretty much a summary of everything we just now said. So when we estimate a regression equation using a sample, it looks like this. Y hat equals beta naught plus beta 1 times X. And mathematically, regression tries to find the best values of beta naught and beta 1 that allows us to predict Y using X. So that's just a fancy way of saying regression finds the line of best fit. That's just a fancy way of saying regression finds the line of best fit because our line is defined by beta naught and beta 1. Our line is defined by beta naught and beta 1. Okay. And then this is just a caveat to kind of dig into that a little bit more, is how do we define best? Typically, we're using regression. We define best as the equation that will give us the smallest deviations or the smallest differences between our observed values and our predicted values. So when we calculate a regression, the best line is typically the line that gives us the smallest difference between our observed values and our predicted values. You don't need to know this formula, but it is calculated by the formula, the sum of our observed values minus our predicted values squared. So it's the sum of squared differences between our observed values and our predicted values. And this is often called the sum of squares due to error. This is often called the sum of squares due to error. And you can see a visual demonstration of it in this figure right here. is one way to think about it. It's just like we talked about the correlation a week ago. Is regression finds the line that's the smallest sum of deviations from your observed values. So if you were to draw any other line, you would have a greater difference between your observed values and your predicted values, or your line. So therefore, this is the smallest sum of squares, or the smallest deviations from your observed values. And I know this might not help, but if that helps, then good. If not, don't worry about that part. If that just confuses you, don't worry about it. But if that helps you understand regression, then I'm glad. Okay. So fortunately, whenever you run a regression in any stats program, Excel, Jamovi, SPSS, R, whatever, the stats program will automatically calculate this line for you. It automatically gives you the regression results. They give you the smallest sum of squares due to error. Your stats program will automatically give you your line of best fit, or the regression results that give you the line of best fit. And then once again, if you were to draw any other line on that chart, it would have a worse sum of squares due to error. So whatever the program gives you is the line of best fit. Okay. And there's another visual illustration. If that helps you, go back through the PowerPoint, look at it yourself, but that's as far as I'm going to cover it. So if you want to look at it more, it's there. If not, don't worry about it. Okay. Also, another thing to note is that regression will not only give you your beta naught, and not only will give you your beta 1, but it'll give you something separate that is your r squared. It'll also give you an r squared value. So it's going to give you your beta naught, it's going to give you your beta 1, but it's also going to give you your r squared value. And your r squared value tells you how much variance in your outcome is explained by your predictors. Your r squared value will tell you how much variance in your outcome is explained by your predictors. Oops. So pretty much this just tells you how well do your predictors explain your outcome. So your r squared gives you an overall estimation of how well your predictors explain your outcome. It doesn't necessarily tell you, if you were to try to predict that outcome, how many times are you going to correctly predict it. It does not tell you that. So once again, it does not tell you an estimation of how many times you can correctly predict your outcome based on your regression. Instead, it gives you an estimate of just how much variance do you explain in that outcome. And instead, it just gives you an estimate of how much variance can you explain in that outcome. So if your r squared, let's say it's 0.1, that means you can explain 10% of your variance in your outcome based on your regression equation. But once again, that doesn't necessarily mean that you're going to be able to predict your outcome 10% of the time. Instead, it just means you're explaining 10% of the variance in your outcome. Okay. And then the other thing to note about your regression results is your regression will also give you a p-value for each predictor. So your regression will also give you a p-value for each predictor. So this will tell you whether each of your predictors are statistically significant. So we get a beta naught, we get a beta 1, but then we also get a p-value for each predictor, in addition to the overall r squared. So once again, in summary, if you run a regression with just one predictor, you're going to get your beta naught, you're going to get your beta 1, and you're going to get a p-value for that predictor. And then lastly, you're going to get an r squared that tells you the overall amount of variance your predictor explains in the outcome. Okay. And then also, your p-value functions just like you did for a correlation. Your p-value functions just like it did for a correlation. If your p is less than 0.05 for a predictor, that means it's a statistically significant predictor of your outcome. So once again, if a p that's associated with a predictor is statistically significant, if your p is less than 0.05, that means that this predictor is a statistically significant predictor of your outcome. Whereas if p is less than 0.05, that means it's a not statistically significant predictor. Sorry, that's a less than, I meant to say greater than. If I messed that up, sorry. So if p less than 0.05, statistically significant. If p greater than 0.05, not statistically significant. So if p is less than 0.05 for your predictor, it's a statistically significant predictor. If p is greater than 0.05 for your predictor, it's not a statistically significant predictor. So just like correlation, just like correlation. Hopefully I said it correctly that time. Okay. Also, most software packages will give you standardized and unstandardized betas. Just for your knowledge, standardized betas are just to give you a feeling of how big the effects are, no matter the unit of measurement. Unstandardized betas are for prediction. So unstandardized betas are used for what we're doing over here. So if you want to try to predict your outcome, you're going to want to use your unstandardized betas. We already talked about that. Whereas standardized betas are to give you an overall estimate of how large is the effect. So unstandardized betas are used for prediction. Unstandardized betas are used for what we did over here. Whereas standardized betas are to give you an estimate of the size of the overall effect. So standardized betas are easier to interpret, whereas unstandardized betas are harder to interpret. And in this class, I'm not going to make you remember any benchmarks for your standardized betas coefficients. I'm not going to make you remember any benchmarks for your standardized beta coefficients, but just know that in general, standardized are easier to interpret. There are more standard benchmarks for those across fields, just like a correlation. So therefore, we tend to report both your unstandardized betas, if you want to do prediction, as well as your standardized betas for prediction purposes. Okay. We already talked about how we use those for prediction, so but this is here for an example if you want to review it yourself. Okay. So are there any questions at all with regression with two variables? Are there any questions at all for regression with two variables? Any questions at all? Okay. I know we're speeding through this. I'm trying to crunch some stuff together. So I apologize for going through it so quickly, but we kind of have to. Okay. So let's go ahead and take an 8-minute break, and let's meet back again at 7:05. So let's take an 8-minute break, and we'll meet back again at 7:05 to cover the rest of regression and quadratic regression.
Oh, yeah, was it the email or just? Okay, yeah, there it was. There's just one called Regression. And did you figure out? I didn't get that far. But when I had time, I was like, oh, this is the issue I was having because. Yeah, I looked at it,
Okay, let's go ahead and get started with the last part of class. Let's go ahead and get started with the last part. Okay, so we good in the back? Okay, good in the front. Awesome. Good in the back and good in the front. Good, very good. Okay, so the main things I wanted you to take away from what we were talking about regression before is that we run a regression. It gives us a regression equation that represents a line. So our regression equation represents a line. So then from our regression equation, we have beta naught, which is the intercept, beta 1, which is the slope. So we can look at our beta 1 and see what is the direction of the relationship between x and y. We can look at our beta 1 to know what the direction of the relationship is between x and y. So once again, beta naught, intercept, beta 1, the slope. Also, we're going to get a p-value associated with our x of 1, and our p-value will tell us whether that relationship is statistically significant or not statistically significant. P less than 0.05, statistically significant. P greater than 0.05, not statistically significant. And then lastly, we get an r-squared value, which is how much of the variance our predictors explain in the outcome. So r-squared, how much of the variance our predictors explain in the outcome. Okay. Any questions come up during the break about regression? Because I know that's what you were talking about because you're so excited about it. Okay. All right, so now we're going to briefly cover multiple regression, but if you understood everything I said right here, then you'll understand multiple regression. Multiple regression is pretty much the exact same thing. So more commonly, we use regression to estimate the relationship between multiple predictors and a single outcome. So more commonly, we use regression to look at the relationship between multiple predictors and a single outcome. So whereas before, we were just looking at the relationship between x and y, typically with regression, we're going to do multiple regression, which is looking at multiple predictors predicting y. And typically we notate this as x of 1, x of 2, x of 3, for example, all the way to infinity if we wanted to, and all of them predicting y. So once again, regression is a predictor or multiple predictors predicting an outcome. So we might have x of 1, x of 2, and x of 3, all predicting y. One example, and this is an example of true predictors, might be something like what's the relationship of conscientiousness and job satisfaction on job performance. So in this example, we might have both conscientiousness and job satisfaction predicting job performance. And if that was the case, we would know regression would be a perfect tool to analyze that because we have multiple predictors, we have two predictors predicting one outcome. We have multiple predictors predicting one outcome. Okay. So multiple regression follows the same logic as regression with two variables. So it's pretty much the same formula. It's just expanded. I'll go ahead and erase this. It's pretty much the same formula, but it's simply expanded to account for these other predictors or these other variables. So therefore, we had the formula before, y hat equals beta naught plus beta 1 x1. When we're doing multiple regression, we just add additional betas and x's to represent how many variables we're looking at. So if we're looking at 3 predictors, we would then have beta 2x2 plus beta 3x3. So the only difference is for each variable you add, you need to add another beta and another x. So if we have 3 predictors now, we still have beta naught. You always only have one beta naught, but then we have beta 1 x1, beta 2 x2, and beta 3 x3. So therefore, if we have 3 predictors, we would have a total of 4 betas, including beta naught, and then 3 x's. Also, I'll go ahead and note that, like we said before, we're going to have a p-value associated with our beta 1. We're also going to have separate p-values for each of the other betas. We're also going to have separate p-values for each of the other betas. So we might run a regression. We might get something like p for beta 1, or sorry, p for x1 might equals 0.04, p for x2 might equals 0.17, and p for x3 might equal 0.50. You're going to have different p-values for each of your predictors. You're going to have different p-values for each of your predictors. So if this is our case right here, can someone tell me how we interpret our results? So if this was our results right here, a p of 0.04 for x1, a p of 0.17 for x2, and a p of 0.5 for x3, what would we say about our results? Exactly correct. We would say that only x1 is a statistically significant predictor of y, whereas x2 and x3 were not statistically significant predictors of y. So we would just say that x1 was a significant predictor, whereas x2 and x3 were not statistically significant predictors. Like I mentioned before though, we're still going to have only one r squared value. We're still going to have only one r squared value. Still only going to have one r squared value. This will go a little bit beyond what I was planning on covering, but we'll go ahead and cover it now. So let's say we ran our initial regression. Let's say we ran our initial regression with just one predictor, with just x1, and let's say our r squared was 0.1. Let's say our r squared was 0.1. And then let's say we run a regression with all three predictors, and now our r squared is 0.11. What would we say about the variance explained about predictors 2 and 3? What would we say about the variance explained about predictors 2 and 3 if this was our r squared for just the first predictor, and this was our r squared for all three?
Probably not significant. They probably don't have a big impact.
Yeah, that's a good way to put it, yeah. That they didn't have that big of an impact beyond the first predictor. They didn't have a big impact beyond the first predictor. Because with just one predictor, with just this first one, we explained 10% of the variance. When you had 2 and 3, it explained 11% of the variance. So this we can infer that 2 and 3 only explain 1% of the variance in the outcome beyond this, beyond our first predictor. Because with our first predictor, we explained 10% of the variance. When we added 2 more, it only bumped up to 11. So therefore 11 minus 10 is 1. So we would say that these two only explain 1% of the variance beyond our first predictor. Only explain 1% of the variance beyond the first predictor. So, okay. Any questions about that so far? About the betas, about the p's, about the r squares? Okay. Yeah, so when we use regression to estimate the effect of multiple predictors on one outcome, it provides us a linear relationship of each predictor, but it also provides a linear relationship for each predictor while controlling for all the other predictors. So this is why we started with partial correlation, because when you have multiple regression, it serves a lot of the same function as partial correlation. So therefore, we might have this, once again, as a Venn diagram. We once again have y over here, and then we might have x of 1, x of 2, and x of 3. So a regression will tell us how much of the variance is explained by each x, but it also controls for the other x's. So therefore, it will tell us how much each x predicts uniquely of the outcome, but then it also controls for the other x's, and it tries to partition this variance. It'll try to partition the variance, and to try to split it between the predictors. Appropriately. So therefore, you might have a predictor that explains something pretty strongly, but then when you account for other predictors, its explanatory power might weaken. Because its predictive ability might overlap then with these other predictors that explain the outcome better. So just like with partial correlation, like we covered about an hour ago, regression will look at the relationship while controlling for the other variables. Regression will look at these relationships while controlling for the other variables. Okay. But based on what you know about partial correlation and regression, what's one big difference about how they look at that shared variance? What's one big difference between how it looks at the relationships between partial correlation and regression?
It's looking at like causes,
Sorry, say it again.
individual like causes.
Yeah, I think that's what I'm looking for, is that with partial correlation, we are only looking at something like the relationship between x and y while controlling for the others. Regression will tell you all the relationships in one analysis. It will tell you the relationship of x1 while controlling for 2 and 3 on y. It'll tell you the relationship of x2 on y while controlling for 1 and 3. It'll also tell you the relationship of x3 and y while controlling for 1 and 2. Whereas partial correlation, like we said before, if you wanted to get all those relationships, you would have to run partial correlation after partial correlation after partial correlation. Regression will tell you all of these relationships while controlling for all their variables and one analysis. You only have to run the analysis once to get all of those relationships while controlling for all of those other variables. And that's another thing that makes regression so useful. It can allow us to look at multiple relationships at the same time while controlling for all the other predictors. So it's very useful.
Is there a situation where you have multiple variables where you use partial correlation of a regression?
That is good. So the question was, is there a situation where you would have multiple variables where you use partial correlation over regression? I'm trying to think.
It seems like with regression, you already have the dependency built in, so you don't have to worry.
Yeah. So the question was, is there a situation you use partial correlation over regression? I can see some situations that if you're particularly sensitive to wanting to not look at causality, if you're thinking you're absolutely not able to look at directional relationships, then maybe you would want to use partial correlation. I will say that in all of my practical experience of working with companies and also a lot of my research, the default tends to be to just use regression in my experiences. So you're right on that. I'll think about that more. Though. So good question. Any other questions or comments? Any other questions or comments?
One in the chat.
Sorry, what's that? Can all these things you're working by hand be solved in Excel? Yes, all these things we're doing by hand can be solved in Excel. So Excel can run your regressions. So Excel can do all this, but also what we were doing before with prediction. I sent you a link to mattchauer.com that shows you how to do regression with prediction in Excel. So all this can be done in Excel. So good question, Lexi. This can be done in Excel.
So what is it that can't be done? Because isn't that why we have Jamovi as well?
Yes, so Excel cannot do Chromebox Alpha. So you do need Jamovi for Chromebox Alpha. And there might be one or two other things later in the semester. Yeah, so good question. Pretty good question. Yes.
Is there a graph for multiple regression?
Is there a graph for multiple regression? That is a good question. So question for the class. Is there a graph for multiple regression? Just curious to see if anyone can give an answer.
I would assume so.
You would assume so. So anyone want to expand on that or?
Would it just be
Well,
like
it says
multiple
the
lines?
estimate of the linear effect of each predictor, so.
So it would not be multiple lines, good guess. And you said, say it again?
I'm just reading the definition, that it's the estimate of the linear effect of each predictor.
Mm-hmm.
So, I mean, it's got to be a way to show that, to visually show that linear relationship. Wouldn't it be?
There is up to an extent. So does anyone know what that extent would be? I know this is a hard question. I'm just curious.
4 variables?
Not 4 variables. Good guess. Not 4. Any other guesses? 3. Yeah, who said that? 3. So if you have one outcome and 2 predictors, you can visually demonstrate one outcome and 2 predictors. You can visually demonstrate one outcome and 2 predictors. So with looking at what marker would work. Give me 1 second. So with looking at one outcome and 1 predictor, we had something like this, x and y. Let's say it's x of 1. If we wanted to visually add another predictor, we wanted to visually add a second predictor, how do we do that?
Another dimension.
Yeah, with another dimension, exactly correct. And then we would add another dimension. And I'm a terrible artist. I'm god awful at drawing. Let's see if I can do this. So we'll make it a 3-dimensional chart. And then x2 would be that additional dimension.
Put an arrow at the end.
Sorry, we're at?
Put an arrow at the end of it to make it look like it's going in perspective.
Yeah. Maybe like, yeah, so that works. That's good, yeah. And then we would draw our regression line and imagine this is going through 3D space. So it would look like that. So there are some stats programs you could actually make like a 3D model, and it lets you like point and drag and rotate the model. So you can actually do this very well at certain stats programs. Once you get beyond 2 predictors, you can't really visualize it at that point. Once it's beyond 2, because once you get into like the next dimension after that, it's like time and then yeah. So you can visualize it up to 2 predictors. Anything beyond that, you just have to look at the formulas. Yeah, so very good question. Very good question. And very good answers. I'm very impressed. Okay. Any other questions or comments at this point? Okay. So regression looks at the linear relationship of each predictor while controlling for all the other predictors, so we established that. So therefore, if we're interested in the relationship of the example we used before of conscientiousness and job satisfaction predicting job performance, we ran a regression where we had both of these predicting job performance. It would give us the relationship of conscientiousness on job performance while controlling for job satisfaction. It would also give us the relationship of job satisfaction predicting job performance while controlling for conscientiousness. So it gives us each of these relationships we might be interested in. Okay. And then just like with regression with one predictor, once again, we define the best line that will give us the smallest difference between our observed values and our predicted values. So if we only have two predictors, we can still visualize that as the differences between each point in the line. However, once we get beyond two predictors, we can't visualize that anymore, but it's still the same process. It's still the same process. Okay. And we already established we still get p-values for each predictor. We could also get confidence intervals for each predictor. We still get standardized and unstandardized betas for each predictor. Still, unstandardized betas are used for prediction. Yeah, unstandardized betas are used for prediction. Standardized betas are used for interpretation. And we can still use, that should just say we can still use these unstandardized betas to make predictions. Okay. And then the last thing I wanted to mention about it is that one very common practical application of multiple regression is we see it all the time in personnel selection. We see it all the time in personnel selection. And if you think about how personnel selection works, you might go through and erase some things. I'm trying to erase all this. So one way to think about it is personnel selection, or one common instance of multiple regression is personnel selection, where if you are applying for a company, that company has already collected a data set using its predictors, using whatever it uses to select its employees, if it's a good company, that is. If it's a good company, it's already gathered a data set where it's looked at the predictors that they use for selection purposes. They've already got performance data on the employees they selected, and they made a regression equation based on those predictors and the performance data they have. So they might have a regression equation that looks something like this. Let's keep it simple. So they might have ran a regression using each selection tool they use. They got performance data from their employees, and they got this regression equation. So therefore, whenever they get a new employee, they're going to want to try to predict what your performance would be on the job. What selection is all about is trying to predict what your performance would be on the job. So how selection often works is you take your regression that you estimated, and if you have someone apply, you take whatever X of 1 was, let's say this is their personality test. On the personality test, they scored a 5. The next person, this is the interview score, or sorry, same person, this is their interview score, they scored a 1. And then the last part might be what school they graduated from, and they got a 4 on that because they went to a pretty good school. The next person you would give the same selection tests to. So once again, personality, maybe they really suck at personality, but they really nailed it in the interview. And then they went to an okay school. And then last person just did terrible at everything. So then how selection systems would work at a lot of companies, if they have done this process, which hopefully they should have, is you then take each of your scores, multiply it by the associated beta value for each person, and then each person gets a total score at the end, and you select the person that had the best total score based on how it should be weighted, which is determined by your beta values. So therefore, in this example, I think it's going to be in this person, that even though they sucked at one part, that part wasn't that great of a predictor of job performance. It really was your interview score that was the best predictor, and therefore it's going to be weighted the most. So therefore, this person gets selected. So at a lot of companies, that's how the selection system works, or that's how it should work, and it's all based on regression. Okay. So that is all I wanted to cover about multiple regression. Any questions or comments about multiple regression?
You said unstandardized data used for prediction, standardized data used for what?
Interpretation, yeah. So unstandardized betas are for prediction. Standardized ones are for interpretation purposes. Any other questions or comments? Okay, so let's cover the last part, and this is quadratic regression. So let's go ahead and cover quadratic regression, and this should be relatively short because it's regression. You all seem to understand regression, so good job on that. Okay. So we already covered this. Regression tries to find the test statistics that best describe the relationship between a predictor and an outcome. When there's more than one predictor, it does it for each predictor and each outcome. And everything we've covered so far is for linear relationships. Everything we've covered so far with regression is for linear relationships. However, regression can also test for nonlinear relationships. Regression can also test for nonlinear relationships. And we see these all the time in business. We see these all the time in research. So regression is an extremely powerful tool because it not only can look at linear relationships, but it can look at any type of relationship between an x and a y variable, or an x1 and x2 and x3 and a y variable. So regression can test quadratic, cubic, various other relationships. So if two variables have a nonlinear relationship, we can still test it with regression, and perhaps more importantly, we can still test the linear effect, a nonlinear effect, and we can still control for everything else that we want to. So we can still test for linear effects, we can still control for things while in the process of assessing these nonlinear relationships. Okay. So therefore, if we think two variables have a relationship that looks something like this, we could test that with regression. We could do that super easy with regression. We could tell regression to estimate a line that has two curves in it. We could throw it in our regression equation and see if it works. Once again, here's another version. We could run a regression to look at that, where we see, is there a certain point that's like the inflection point, where suddenly the two variables have a very steep slope. Regression can test that. Once again, regression can even test something as complicated as this. This is a sine wave. You can see if the relationship between x and y is described as a sine wave. We can do that with regression. It's pretty easy. So therefore, to get a taste of nonlinear regression, we're going to learn about quadratic regression. And this will probably be the only type of nonlinear regression we're going to cover this semester. So it's just to get you exposed to some of the principles of nonlinear regression. But be aware that the process to test for other types of nonlinear regression are very similar. The process to test other types of nonlinear regression are very similar. So if you ever need to use nonlinear regression after this, you shouldn't be scared of it. It should not be a scary thing, because you've already done one type, you've already done quadratic regression. So if you need to do any other type, you should be able to do it yourself. Okay. So therefore, quadratic regression is used to identify the strength and direction of a relationship between a predictor and an outcome when we believe the relationship has a single curve. And this is very important. So whereas before linear regression would look at a straight line, quadratic regression is when we think the relationship between an x and a y variable looks something like this. We think the relationship might be described by a single curve. And that's when we would use quadratic regression. Or the curve might look like this. That could also be a use of quadratic regression. So if we think the relationship between x and y is described by a single curve, we would use quadratic regression. And the curve also doesn't need to be that dramatic. The curve could look something like that. Still just one curve, it just ends early. So therefore, linear regression, straight line, quadratic regression, single curve. Okay. And the formula for a quadratic regression, that should not be beta 2 beta 1s. The formula for quadratic regression is y hat equals beta naught plus beta 1 x1 plus beta 2 x1 squared. That's the formula for quadratic regression. So that should not be 2 beta 1s. That second beta 1 should be a beta 2. So it is y hat equals beta naught plus beta 1 x1 plus beta 2 x1 squared plus beta 2 x1 squared. And I'll give everyone a sec to write that down since the PowerPoint slide was incorrect. So once again, y hat equals beta naught plus beta 1 x1 plus beta 2, so that's 2, beta 2 x1 squared. I think everyone has it now? Okay. And once again, this is a visual demonstration of what your regression line might look like when running a quadratic regression. Okay. Most commonly, we use quadratic regression when we think there's something called a too much of a good thing effect. Most commonly, we would use quadratic regression when we think there's too much of a good thing effect. The quadratic regression is often used when we think that an x variable might positively impact a y variable up to a certain extent. That once this x starts going up, it's good, it's good, it's good, we're happy, but then suddenly you're going to reach an inflection point where too much is a bad thing. You have too much of a good thing. So therefore, adding after a certain point becomes a bad thing. And therefore, after this inflection point, your y starts going back down. And that's considered the too much of a good thing effect. And once you get a certain inflection point, it stops becoming a positive, it starts becoming a negative. So an example of this might be, like we keep on talking about, the relationship between conscientiousness and life satisfaction. I guess this is slightly different, but conscientiousness and life satisfaction. If you're someone who's hardworking, someone who's diligent, someone who's detail-oriented, that's conscientiousness. If you're someone who has those characteristics, you might have higher life satisfaction up to a certain extent. Because you're motivated, you're probably going to have a better job, you're harder working, people are probably going to like you more, you're detail-oriented, so you're probably going to do better in classes, so you're going to have higher life satisfaction up to a certain extent. But then if you're too conscientious, you might be OCD. If you're too conscientious, you might be too motivated, where you start getting stressed out about everything. So therefore, if you have your conscientiousness reach a certain point, it might be too much of a good thing, and your life satisfaction starts going down. Your life satisfaction starts going down. And we could never test that with just linear regression. We could never test that hypothesis with just linear regression. We need to use quadratic regression to see, is there too much of a good thing effect between conscientiousness and life satisfaction? Because quadratic regression can test the single curve, whereas just linear regression alone cannot. Okay. So how do we test it? So to perform many nonlinear forms of regression, you simply transform your predictor values. So for many nonlinear forms of regression, you simply transform your predictor values. And for quadratic regression, you just simply square each participant's value of the predictor. So for quadratic regression, you simply square each participant's value of the predictor, or on the predictor. So once again, for many nonlinear forms of regression, you just transform your predictor values. And for quadratic regression, we're just going to square them. We're just going to square them. Okay. And we're going to walk through a quick example. I know I don't normally do this, but I want to point out something important with this. Is we might start off our data set with this. We might start off our data set with this of just an x variable and just a y variable. So we might have just an x and just a y, and we want to test for the quadratic effect between x and y. So to do this, I said we need to transform our variable, we need to transform our x, but we don't want to replace our original x values. We do not want to replace our original x values. And this is extremely important. This is extremely important. So therefore, we would make a new column. That would be x squared, because we do not want to replace our original x's. So we make a new column that's x squared, and we would square the values in that column. We would square the values in that column. So now we still have our original x values, but now we also have our x squared values. Now we also have our x squared values. And once we have that, back up a little bit. Once we have that, we would simply run a regression where y is our outcome variable, and we would include both x and x squared as our predictors. We would include both x and x squared as our predictors. And that's also very important that if you run a regression, if you run a quadratic regression and you only include x squared, you're going to get incorrect values. You're going to get incorrect results if you only include x squared. So when you're running quadratic regression, you want to have your outcome, and you want to include both x and x squared when doing quadratic regression. And then based on that, you might get a result that looks like this. You might get a result that looks like this, where we would get separate results for both our x and our x squared. You get separate results for both your x and your x squared. So typically when we're doing quadratic regression, if our x squared value is significant, well, first off, that means we have a significant quadratic effect. If our x squared is significant, that means we have a significant quadratic effect. That means that our relationship between x and y is described by a single curve. So therefore, we would celebrate because our quadratic regression is significant, our x squared was significant, so therefore the relationship between x and y can be described by a single curve. I guess I should have done that. Okay. If that is the case, if our x squared is significant, we typically then do not interpret just our x value. We typically then do not interpret just the linear effect. If our x squared is significant, that means we have a significant quadratic effect, and then we don't worry about interpreting the linear effect because the quadratic effect was significant. That's the one we're interested in. So therefore, we don't interpret the linear effect. We therefore then only interpret the quadratic effect if this quadratic effect is significant, if it is indeed significant. If it's not significant, we would then still go back and look at the linear effect. But if it is significant, we just ignore the linear effect.
So
Yes.
is there something in Excel that we would get those numbers?
Yes.
Okay.
Yes. So if you go through and this week do the guides for regression or quadratic regression, it's going to show you how to get these numbers. Yep. So good question. I guess I forgot I didn't cover that. So thank you for pointing that out. Yeah. Excel will give you all this. Jamovi will give you all this. So yep. Good question. Okay. So therefore, if you get results that look like this, if your x squared is significant, that means you have a significant quadratic effect, and you ignore the linear effect. If your x squared is not significant, then you would go ahead and take a look at your linear effect. You then would go ahead and take a look at your linear effect and see if you do have a significant linear effect, but only if your x squared is not significant. Okay. Any other questions? Any other comments?
Can you just like say that one more time?
Yeah.
Just go back to that.
How do you determine, how do you determine if it's significant?
Yeah. So this is our regression results. This is what our regression results will look like in Excel. So I guess let me back up. Let's back up for a second. So if this is our regression results in either Excel or Jamovi. So this right here would be our beta values. This right here would be our beta values. So this tells you the direction of the relationship. So this right here is our beta values. And then this is our, like we talked about last week, this is the asterisk representing our p-values. Those are our asterisks representing our p-values. So if Excel or Jamovi gives you asterisks associated with a certain row, that means that row is statistically significant. P is less than 0.01? Yep, that's correct. Because in this example, P would be less than 0.01. In this example, P is less than 0.01. So in this example, we have these significant asterisks right here. This row right here represents our quadratic effect. Because our quadratic effect is the x squared. Our quadratic effect is associated with x squared. We had significant p-values right here. So this means our quadratic effect is statistically significant. So if our quadratic effect is statistically significant, then we can just ignore the linear effect. Then we don't interpret the linear effect. We just say it's a significant quadratic effect. Our x squared is significant. So this relationship is described by a single curve. And we just ignore our linear interpretation if this is significant.
In Jamovi, it tells you those, it reminds you about the stars.
Does it? Okay, good. Very good.
Chart of them.
Yeah. So yeah, and that's a good point. Is Jamovi does give you more details. So if you're doing this in Excel and you're like confused, you might want to go ahead and do it in Jamovi too, because Jamovi does give you more annotations. So that's a very good point. Okay. But let's say we run this, and let's say that our x squared, let's say these asterisks are not there. Let's say our x squared asterisks are not there, and there's no asterisks whatsoever for our x squared row. That means our quadratic effect is not significant. If there's no asterisks over here, that means our x squared is not significant. So therefore, since this is not significant, we then would go ahead and interpret our linear effect. We then would go ahead and interpret our linear effect. We would go ahead and say, oh, look at that, our x was significant. So that means even though our quadratic effect was not significant, there was a significant linear effect. There was a significant linear effect. And this is only true for quadratic regression. This is only true for quadratic regression. And if you were to get into cubic, quartic regression, it would be true for those, and we're not going to cover those in this class. This concept right here of ignoring linear effects is the only thing we're going to cover in class where you would ignore that type of effect is quadratic regression. So once again, the only thing we're going to cover in class that we would ignore a significant linear effect would be quadratic regression, and it only occurs if your quadratic effect is statistically significant. So therefore, if we were looking at just basic regression, and we have y hat equals beta naught plus beta 1 plus beta 2 x2, and let's say if we're just doing normal linear regression, and these are different predictors, these are separate predictors, and if both of these were significant, then we would interpret both of those significant effects. If that's just basic linear regression, if this is just normal linear regression, and we have two separate predictors, and both of these are significant, we would interpret both of those linear effects. We only ever ignore a significant linear effect is if we're doing quadratic regression, and our quadratic effect is statistically significant. That's the only time we wouldn't interpret the linear effect, is only when your quadratic effect is statistically significant, and only the linear effect associated with that quadratic effect would be ignored. Okay, I know that's a lot. So are there any questions, comments, insights? Yes?
What is T stand for?
Yeah, so T, that's a part of the output you're going to get in Excel and Jamovi. The only thing you need to know about that is that goes into calculating your p-value. The only thing you need to know about that is that goes into calculating your p-value. You don't need to know how to interpret that. You don't need to know how to understand that. Just know it goes into calculating your p-value. So therefore, most of the time in Excel and often in Jamovi, you'll find your significance, or you'll find your asterisks next to your t-values. That's very common in some of these programs. Not always, but that is common. So good question, very good question. Any other questions or comments? Once, going twice. Okay. Okay. Yeah, so like I said before, even though we're only going to cover quadratic regression, even though that's the only nonlinear form of regression, I encourage you just to play around in Excel and see what other types of regression exist. Do the same in Jamovi. There's tons of different types you can mess around with. You can test with any relationship using regression and transformations. So that's up to you. But we are only going to cover quadratic regression as a form of nonlinear regression. Okay. There's also this at the end of the PowerPoint. I'm not going to cover it, but if you're interested in why does this work, the short answer is geometry. So if you're interested in why can you just square a variable, why can you just get x squared and test a nonlinear relationship, the short answer is geometry. The longer answer is in the back of the PowerPoint. So if you're interested in that, go through the PowerPoint. It explains it very briefly, but that's there for you. So, okay, that's all I have for today. So thank y'all for hanging in there. I know that was a ton, so thank y'all for paying attention. I'll be around for a little bit if you want to start doing this in Excel, if you want to start doing this in Jamovi. Otherwise, you're free to leave. Shoot me any emails if you have any questions, and I'm always happy to help out with anything whatsoever. So thank y'all.
I did have a question on, I was going through like a website, and where it says the p-value has 5 p-values.
Yes.
How do you interpret I mean,
Yes.
Okay,
Okay, yeah. Do you have your other numbers here, or is it just you?
Well, I think one of the ones you call them.
Okay, yeah. Yeah, that works.
I need some help with the Chromebox.
Chromebox Alpha?
Yes.
Okay, what do you need help with it?
I was looking like through the, like, I went to your website, like, went to over there, but I still like, I just don't get it, like how to do it
Okay,
with the data that we have.
okay. What would help you figure it out?
An example maybe, or just like a little like, how do I start?
So have you tried to pull up the guides and use like the example data sets?
Yeah.
And they didn't help?
Not really.
Okay.
Because in the data set, there's only like 3, and then the other one's like,
Okay, yeah, I see what you're saying. So I'll say, first off, I'll just give you general advice right now, and then if you still need help, just send me an email, and I'll think of examples that can help you. But you're gonna want to run the Chromebox Alpha separate for each variable. So if your variable has 8 items, then you just include those 8 items and run it for that construct. And then the next construct, if it has 6 items, you put those 6 items in and run it for that construct. So on the homework, you're going to end up doing, I think it's 4 separate Chromebox Alphas. And then when you do it, make sure you do not include the scale averages. Don't include the scale averages.
yeah. And also, because I also like look online, there's a way that you can do Excel, and the way that you do manually.
You certainly could. It's much harder, but
Yeah.
you could if you wanted
I had
to.
to plug in more.
Yeah. But yeah, shoot me an email. Definitely shoot me an email, and I'll think of like other ways that might be better explanations, and I'll definitely help you out.
Okay, also, there's also a program called like Mathematica. I'm not sure if
Okay.
you've heard of it.
I've heard of it.
Alpha.
Yeah.
Yeah, and I think that program has like all of these like regressions,
Okay.
regressions and all that. Because I had that topic in my bachelor's in mathematics. So if I feel comfortable using the program, can you just use that?
Yeah, you definitely could. Yep. I wouldn't be able to give as much help if you're using that program because I don't know that program. But yeah, you definitely could. That'd be perfectly fine. Yep.
Okay, perfect. Thank you.
Yep. Thank you.
So, are you?
I think what y'all were talking about, that's why I tried to come up. Okay, and I think I was getting confused because I was trying to include too many different items. So, like this, I heard you saying do all of them that are included in that set. So like for satisfaction, I'm gonna do.
See, they'll bring some more around.
And then I'll stop,
All the years that we collected.
because then that goes into the other stuff. I also don't want to include those averages. But then on the other note, you said do just the average, which makes sense because I was thinking, I'm like, if I'm looking at satisfaction versus whatever else, I'm like, I got like 50.
Yeah, exactly. Yeah. Yeah. So you got it. Yep.
One day, 5 million things going on.
You remember we were in a group that did the whole like planning data for,
National championships.
yes, if it changes to revenue for the programs or the donations and stuff. And we still are not super confident about the whole data analysis part of it. So I can just give an example. So it's going to be an example of the expenses. All the sport programs combined. But that was go up, let's get them out of the data, all different years. So what it is, the first question is used about that system, Emma Williams, 2017. That is one single data. How can you compare that one data point to one data set?
The best easiest way to do this.
If I was just overthinking
Because there's a lot of companies where you can read the data.
That's what I was surprised, because that's not always easy, but I know she said at some point, we have to like.
Out of here, it is free, and here,
You can't
and
just
then
answer that.
Because like the way this one is normal, if you were to do this like the most correct way, you guys would be able to model modeling, but we don't. It is. I definitely don't know how to do it. Not to be able to do it until you have to read through it. Look at everything. Sorry, I don't have to take off this. Can you do me a favor, just send me an email with this data set, and I'll look at it and I'll play around with it, and then I'll let y'all know.
now that I know that,
Most correctly would be on all the but I'm not sure to do myself.
I guess we're just at this point right now in the group where we found some data out there, but we're not sure yet if we can use this data to write.
And I would hope that you could, if you're more, because this is a lot of data, so like that would be enough to write something interesting.
Right, we would have different calls, we would have the total, revenue, maybe one for total donation,
Yeah.
one for total, how many people apply for this group.
Right.
Have different points.
Yeah, yeah, go ahead and send us to me an email, because I think I know, I think what you would probably end up having to do is you would whereas like, in this case, you
well,
I just have this column here, this column, this column.
And so.
Then we ended up having another column with whether they all want championships that year. You also keep whether they win the championship or for instance.
Stacking them so much, we just take those, you don't have Alabama.
and I can have you girls, I don't care about flavor, I don't care about slime, because she'll stick and contain
Yes, so
those.
it's not the all being the road, I mean, like, it's
No, exactly. So it doesn't just be two columns. For this
Like
example.
everybody was so mad, they're like, "Oh, you should
Okay, I know
be
what
doing
you
it."
mean. We would still keep the header, so no, it doesn't tell us you that.
For now, you would.
I don't even care, I'm like, I don't
Because that's like what makes this a little bit complicated, is that you're completely correct. These are like, one way to think about it is completely independent data sets. If you're wanting to do this and do most correctly, you would probably do.
After a while, it's like,
These relationships separately for each of these data sets, and then aggregate it, and everything in one overall. We're not covering the whole model in this class, though. So therefore, it would probably be, for the purposes. And then just we'll look up running into a
Oh, it is.
modeling is water regression framework. So it's like somewhere here, just not on this person.
And then another problem we have here is that a bunch of these students we collected, like we said, we're gonna have, they're running football championships, national baseball championships, and so on. So if you run LSU against a school that has a good basketball program like Duke, you can't really test against it because they have completely different substance. That's another thing that is.
So what we probably have to do is we would have done, well, after you stack these, column C would end up being like, did they win the football championship that year? Column D would be, did they win the basketball championship that year? Column E would be, did they win the whatever championship that year? And then you can run a regression where you include all three of those as predictors.
In the first.
And it could like, look at the
Move
differences
it to the
together.
top, instead of it being the first row, because otherwise it won't have to.
So it's partially good at that. Well, you're doing not perfectly good at it, but you're partially interested.
Well, I'm just glad you're really confident in us.
Yeah. Like I said, that's a good amount of data. I think this would end up working out, so I think that you're on a good start. I think this would end up working out. So,
Yeah, we will format this for you and try to get this to you by tonight, so you have something to look at.
yeah, that'd be great. That'd be wonderful.
Maybe we can have a better idea maybe on Wednesday if you have more time.
Yeah, definitely, yeah. I think that was- If y'all could, I just wanted to Excel, I would prefer it in Excel, if that's possible. Okay, perfect.
Do you have any more questions?
No, I just want to say I'm sorry that neither did I apply for it didn't start as I was leaving.
It's all good. I hope you're still able to zoom in, so it's all good.
Yeah.
Okay, well, I'm gonna help. I think y'all wanted to be with me, right? Okay.
Thanks so much.
Thank you for answering questions during class.
Yeah. All right, Aaron,